Okay, time for the last set of notes. These include some more complicated problems and a couple more special tricks that will make otherwise difficult problems easier to solve. So the first is subtraction. We have done addition, we've done multiplication. Time for subtraction. So how many 6-letter sequences, which we're calling words, even though they're not actually English language words, contain at least one letter A? So what makes this difficult is there's a lot of different possibilities that you would need to take account for. So if we use P subscript n to describe the number of 6-letter sequences with exactly n A's, then we could say that the thing that we're interested in, let's call it S for sum, so the thing we're interested in would be the number of 6-letter sequences that contain exactly one A, plus the number of 6-letter sequences that contain exactly 2 A's, plus the number of 6-letter sequences that contain exactly 3 A's, and 4 A's, and 5 A's, and 6 A's. And each of these would be its own separate counting problem. Like, how do I figure out how many 6-letter sequences have exactly 5 A's? There's actually only one 6-letter sequence that contains 6 A's, namely the sequence containing all A's. So some of these are going to be easy. So this is one possibility. But these other ones, are maybe a little less clear how you'd count them. And you could think about it, and that would be interesting. But there's a much easier approach. The easier approach is, let's ignore this at least one condition. Let's just say how many 6-letter sequences are there total. So let's do total number of 6-letter sequences. And let's subtract the number of sequences that contain no A's. Because if your sequence doesn't contain 0 A's, then it has to contain at least one A. And each of these things are much easier to count. So the total number of 6-letter sequences. So let's see, you could think about it this way. I've got 1, 2, 3, 4, 5, 6 letters that I have to choose which letter is it going to be. So 6 positions. And then there's 26 letters in the alphabet. So it's like I've got 26 choices for what my first letter could be, and 26 for my second letter, and so on. So that's just 26 to the power of 6. Okay, so how many sequences are there that contain no letter A's? It's the same situation, except now I only have 25 letters to choose from. So I'm still making 6 choices. What's my first letter? What's my second? What's my third? But for each of my choices, I have 25 possible options because I'm not considering the letter A as a possible option. So that's subtraction. The idea is, instead of breaking it apart into a whole bunch of separate things that you have to count more than you want and subtract away the possibilities that you don't actually want to include. Okay, so stars and bars describes another kind of clever technique for solving certain kinds of counting problem. In my example, we will have 7 identically trench-coated people boarding a Siberian train with 4 cars. How many ways can it happen? So my describing the people as identically trench-coated is my subtle way of suggesting that we can't distinguish the people. We can't tell them apart. So it doesn't matter if person 1 gets on train car 1 or person 2 gets on train car 1. It just matters how many people are on train car 1 and how many people are on train car 2 and so on. So here's the idea of stars and bars. Here's my 7 identically trench-coated people minus trench coats. The number of ways of assigning them to 4 train cars is the same as the number of different ways I can draw 3 vertical partitions. And here's the sort of thing I mean. So let's say I drew a vertical partition here, and another one here, and another one here. So 3 vertical partitions is going to create 4 regions. There's the region that's to the left of the first. There's the region that's between the first and second, between the second and third, and to the right of the third. So imagine that this is describing train car 1, train car 2, train car 3, train car 4. So train car 1 contains 2 people, train car 2 contains 1, 3 contains 3, and 4 contains 1. And hopefully it's clear that drawing these partitions in a different ordering is going to produce a different number of people in each of the train cars. So I had said that the number of possible assignments of these people to train cars is the same as the number of ways of drawing these partitions. I'm not going to prove it to you in particular, but I'll kind of suggest the direction that you could think. If I'm trying to claim that these two sets are the same size, I'm going to observe that any way I have of drawing three partitions is going to create a unique assignment of numbers to four train cars. And every assignment of numbers to four train cars can be realized in exactly one way with a set of partitions. So that kind of suggests that there's a one-to-one mapping there. So in a second, I'll show you why this way of thinking about it makes it easier to count. Let's do one more example. So in the first version of this, how many ways can it happen? We're assuming it's okay if some of the train cars are empty. So I just want to show you that that's a possibility with my stars and bars approach. Here, instead of drawing people, I've drawn little tiny stars. And then the bars are still bars. So what if I draw a partition here before the first person? I draw two partitions here and here, and that's all three partitions. So remember, this defines four train car zones. So here, the first train car is empty. It's got 0 people. The next train car has 3 people. The third train car between these two partitions has 0 people. And the last train car has 4 people. So again, I've assigned 7 people into 4 train cars, except the first and the third are empty, and everybody has gone to the second and the fourth. So I just wanted to show you that if you're allowed to draw a partition either to the left of this person or to the right of this person, that gives you a way of making either the first or the last train car empty. And by assigning 2 partitions in the same location between people, you can make the other train cars empty as well. Okay, so how does this actually make it easier to count the number of possibilities? So a tempting but wrong idea would be to think this way. If I have 7 people, that creates 8 possible locations I could place a bar. Let's just count them. So there's 1 here, 2, 3, 4, 5, 6, 7, 8. So if there's 8 positions I could put a bar, and I'm going to put 3 bars, it's like 8 choose 3, is I'm selecting 3 locations to put my bars in from a collection of 8 possible locations. The reason this doesn't work, or at least one of the reasons this doesn't work, is 8 choose 3 requires that the 3 locations be different from each other. So I actually would fail to count this possibility where 2 bars are put in the same location. So that doesn't work. Another tempting but wrong approach to this might be to say, all right, I want it to be the case that I can place the same, more than 1 bar in the same location. So again, I've got 8 possible locations. I'm making 3 choices where to place each bar. So the first bar could go in any of the 8 spots. The next bar could go in any of the 8 spots. The next bar could go in any of the 8 spots. And again, that seems very, very tempting. Here's the problem with this. I've drawn out 2 possible ways of partitioning the 8 objects. So in this way, in this version, I've put a bar in location 3, a bar in location 4, and a bar in location 5. The problem is our approach to counting up here counts this possibility in lots of different ways. For example, I could have chosen my first bar to go in location 3, my second bar to go in location 4, my third bar to go in location 5. Or I could have chosen my first bar to go in location 4, and then 3, and then 5. Or first 5, then 4, then 3. So this is the typical scenario where all of the different orders that I could have placed the bars in these 3 locations all produce the same outcome. So I don't want to count them as different. So now you might be thinking, aha, well, we've seen this situation before. What I really want to do is I really want to divide by the number of reorderings that are the same. So I want to divide by 3 factorial. The problem is that that's dividing by too many things for some of the possibilities. This possibility, my original method of counting, only counts once. Here I put all 3 bars in location 3, so that's 3, 3, 3. So this outcome, I was counting 6 different ways in my original method for counting. But this outcome, I was only counting 1 way for my original way of counting. So if I divide by 3 factorial, that's too many things to divide by for some possibilities, and it's just right for other possibilities. So this seems like a mess because different possibilities are being like over-counted different numbers of times, so there's not a single thing I can divide by. So if you're feeling overwhelmed, like, oh my god, why did we even start thinking this way? Fear not, there's a very clean way of thinking about this. Instead of thinking about positions, instead of thinking about the people being fixed, and we're assigning bars in fixed positions between the people, let's think that we want to take 7 people and 3 bars and put them in some ordering. So 7 people and 3 bars are 10 different things. So let's imagine that we have 10 positions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 3 of these positions we're going to put bars into, and the rest of the positions we're going to put stars into. And that really is going to count the number of different ways of sequencing 7 people with 3 bars. So how are we going to count this? There are 10 total positions, and I'm going to choose 3 different positions to place bars into. So how is this different than this case over here? The case over here, I said, didn't count the possibility where more than one bar could be drawn between 2 people. However, if I have 10 positions and I'm choosing 3 different positions to put bars into, I might, for example, choose these 3 positions to put bars into, and the rest of the positions are people. And that definitely corresponds to having inserted all 3 bars between 2 people. So, for example, in train car 1, we'd have 4 people, then 0 people, then 0 people, then 3 people. So hopefully it's intuitive to you, or if you pause the video and think about it, it would be clear that this actually does count the exact thing that we want. The situation where no train car can be empty is actually a lot easier. Again, imagine we've got the 7 people, only now, when I put down the bars, I can't put a bar to the left of this person, because that would make the first train car have 0 people. And I can't put a bar to the right of the last person, because that would make the last train car have 0 people. And I can't put 2 bars between 2 people, because that would make one of the middle train cars have 0 people. So now we really do have a situation where I've got 7 people, I've got 6 total spots I can put bars. I need to place 3 bars amongst these 6 spots, and I'm not allowed to place a bar, more than one bar in the same spot. So now this really is a situation where 6 choose 3 is going to describe the thing that we want. So that wraps up stars and bars. Here we've got 10 spots, and we're going to choose 3 of them to put bars, and the rest are the stars. Here we've got 6 spots between the stars that are fixed, and we're going to choose 3 of them to put bars in. So I think the essence of this technique is to ask yourself, is my counting problem a problem where I'm trying to assign things to groups? Am I trying to partition a set of things so they all have to add up to the total that I have? And that would be a good candidate for a stars and bars technique. Okay, come back in my last video for an example of how to put a lot of these things together.